Good day, grade 12 learners. Welcome to today's Physical Sciences lesson. My name is Salayolo Murukuladi. This lesson is brought to you by the Northern Cape Department of Education in collaboration with Pakama Research and Development. So today we are going to continue with our paper 1 revision program. Today's topic is wave, sound, and light, and the subtopic is Doppler effect. So by now you are very familiar with the structure of your question paper. Section A, 10 multiple choice questions, 2 marks each, so the total there is 20. And then your longer structured questions will be 130 marks, all in all making up 150. And this exam will be taken obviously over 3 hours. So what are we going to be looking at? Doppler effect in your examination will go for about between 11 and 15 marks. And we will obviously, or you would obviously need to know your definitions. Doppler effect, definitely. Redshift, blue shift, frequency, wavelength, and period, which are things that you learned in the previous grades. So they are also very important. And then we'll also perform calculations. Obviously, calculations will include this. Calculations will include the calculation of frequency or the calculation of period, because we know the relationship between the two. And then we'll also look at the Doppler equation, of course. And then another important section of this is obviously applications of Doppler effect, right? So Doppler effect is used in medicine, it's used in law enforcement, and it's also used in astronomy. We know that you can use Doppler effect to detect the heartbeat of an unborn baby. So that's one of the uses of Doppler effect in medicine. You can also use it to measure the rate of blood flow using something called the Doppler flow meter. So the Doppler flow meter is used to measure the rate of blood flow. And then there's also ultrasound, of course. And then in law enforcement, it's used to detect. Doppler effect is used to detect the speed of vehicles. And then in astronomy, Doppler effect is used to explain why the universe, or claims that the universe is expanding. The universe is expanding. We also have red shifts and blue shifts to explain if whether stars are moving towards or away from the Earth. So yeah, that's what we're going to be looking at in today's Doppler effect revision lesson. Let's get into it. Okay, so our starting point is a question from the Eastern Cape, September of 2018, question number 6. It says, in the diagram below, a police car with its siren blaring stationed between 2 stationary observers. So our observers are not moving. So that already informs our velocity or speed of the listener. First question. How does the frequency detected by observer 1 compare to the frequency detected by observer 2 while the car is stationary? Choose from greater than, less than, or equal to. Now, if there's no relative motion between this car and the observers, then the frequency detected must be equal to. So our answer for this question is going to be the frequency is equal to. The reason for this is there is no relative motion. There is no relative motion between the car and the observers. So they will both detect the same frequency. Okay. In the diagram below, a police car with its siren blaring stationed between 2 observers. The police car starts to move in the direction indicated by the arrow in the diagram. Now, when we look at this arrow, it's clear to see that the car is moving towards observer 1, right? Now, if the car is moving towards observer 1, our expectation is that the frequency detected by observer 1 must be greater than the frequency of the source, right? And then this side, it's obviously going to be the opposite because it's moving away, right? Okay. How does the frequency detected by observer 1 compare to the frequency detected by observer 2? Choose from greater than, less than, or equal to. So it will obviously be greater than. So our answer for question number 2 is simply greater than. Perfect. Okay, let's move on to the next question. The next question says, draw a diagram to support the answer in question 2. Okay, so our best bet is to obviously use waveforms, right? So I'm going to say observer number 1 is this side. This is observer 1. And then there's observer 2. Observer 2 over here. So when I draw my waveforms, this is what I'm going to do. They must be compressed towards observer 1 because the car is moving in the direction of observer 1. So this is the expectation that you are going to have waveforms stretched out on observer 2, and then you are going to have waveforms compressed on observer 1 because the sound source is moving towards observer 1. Okay, let's go to the next question. The next question says, name the phenomenon described in questions 1 and 2 above. So this phenomenon is the Doppler effect. This phenomenon is the Doppler effect. Please be careful. In some instances, the question will say name and describe, right? And then instead of 1 mark here, they'll put 3 marks, meaning that they would expect you to write that it's Doppler effect and then also write the definition for Doppler effect. But in this case, it's just 1 mark, name the phenomenon described above. So we simply say Doppler effect and then we are good to go. Question number 5. Observer 1 registers a frequency. Remember, observer 1 is the listener, right? So he registers a frequency of that much, 1730 hertz. Now, frequency must always be in hertz, not kilohertz, but hertz. As the police car approaches at a constant velocity of 25 meters per second, take the velocity of sound in air as 340. Calculate the frequency of the siren. So you're going to go to your data sheet and say, okay, what is the correct formula here? The correct formula here is FL equals V plus minus VL divided by V plus minus VS multiplied by FS, right? Then let's substitute. This is 1730 equals, they said take the speed of, or the velocity of sound in air is 340. So because this person is not moving, we are not interested in this. This is 0. Whether I put a plus or a minus, it doesn't really matter. 340 minus 25. Subtraction 25 because the source is moving towards the listener, multiplied by Fs. And then Fs in hertz, will work it out, 1730 multiplied by 340 minus 25. All of this divided by 340. Then our frequency of the siren is 1602,79 hertz, and then 5 marks. Probably going to be marked like this. 1 mark for the formula is picked up from the data sheet. 2, 3, 4, and then the 5th mark is for the final answer rather. So that's it. Now, before we move on, let's see if it makes sense. When I started out, I said the expectation is that the frequency of the listener must be more than the frequency of the source, right? 1730 is indeed more than 1602,79. So we are consistent. Okay, the next question I want us to look at is from the Free State, and it's a September question paper of 2019. We are going to look at question 5. It says, A police car is traveling down a road at a constant speed of 16. It emits sound waves from its siren. A man sitting on the side of the road. So this man is sitting. Already we have some idea about the velocity of our listener. Sitting on the side of the road with a detector which registers sound waves at a frequency of 440 as the police car approaches. So when the car approaches, then frequency is 440. After passing him and moving away at the same constant speed, sound waves of frequency 401 hertz are registered. So we are given two frequencies here. So this is the frequency of the listener when the sound source is moving towards. Then we have the frequency of the listener when the sound source is moving away. So this one is for towards, right? So it's important that we make this note so that when we start answering questions, we know exactly where to refer. Okay. Now, first question, state the Doppler effect in words. So there is your Doppler effect. You just state that from the examination guidelines, of course, and then you get yourself an easy 2 marks. Next question for 6 marks, calculate the speed of the sound waves. Calculate the speed of the sound waves. Okay, let's have a look. This question, I have information about what happens when the sound source is moving towards. I have information about what happens when the sound source is moving away, right? So I can set up two different equations, one for when it's moving towards and then one for when it's moving away. And I can work them out simultaneously. So I'm going to start off this side. I'm going to say towards, and let's see how the equation looks. And then this side, I'm going to set up an equation for away. So starting point must always be copying down the formula as it appears on the data sheet. So that's what we have. What is the frequency when the sound source is moving towards? It's 440,74. This equals, we want the speed of sound. So we want this V. So this is going to be V divided by V minus 16 multiplied by Fs, right? Okay. In this case, I want to make Fs the subject of the formula. So Fs is going to be 440,74 open bracket V minus 16 all divided by V. Then this will become my equation number 1. And then what happens when the sound source is moving away? It registers as a frequency of 401,12. And this is going to be equal to V over V plus 16 multiplied by Fs. So Fs is going to be 401 open bracket V plus 16, all of that divided by V. And this becomes my equation number 2. Now, when you look at your equation number 1 and your equation number 2, you would notice something. They're both equal to what? They're both equal to Fs, meaning we can equate them and solve for them simultaneously, right? So we are now going to say equation 1 must be equal to equation 2, right? So our equation 1, we had 440,74 open bracket V minus 16 divided by V being equal to 401,12 open bracket V plus 16 divided by V, right? So I can multiply this side by V, I can multiply this side by V. Then I'm going to be left with, so this does that. So it's 440,74 open bracket V minus 16 equals 401,12 V plus 16. And then I manipulate, and then when I say that one, 440,74 divided by 401,2, then you multiply by that. And then our answer for V is going to be 339,97 meters per second. So this is our speed. So this now becomes the speed of the sound waves. Okay, so the next question says calculate the frequency at which the siren emits the sound waves. So we are looking for the frequency of the source, right? Now I want you to look at these two equations here. This equation represents the frequency of the source. This one represents the frequency of the source. So we can take either of these two, right, and use them to calculate Fs, because now we know our V, right? Okay, let us do exactly that. So I'm going to say Fs equals 440,74 open bracket. What is our V? Our V from the previous slide was 339,97. So I'm going to say 339,97 minus 16 divided by 339,97. And then when we plug that into our calculator, we should get our answer in here. So 440,74, 339,97 minus 16 divided by 339,97. We are getting 419,99. Or if you have 420 heads, that's also fine. This is why this is just 2 marks. So so it's not complicated. It's just a 2-step question, and then you get your answer. Okay, let's move. Okay, grade 12s. The next question that I want us to look at is adapted from the Gauteng September 2022 question paper, and we're going to look at their question 5. Okay, it says grade 12 learners conduct an investigation to verify. So they are verifying the speed of a race car using Doppler effect. A race car driving around a race course at constant speed emits a single frequency of 200 hertz. A learner standing on the final straight records the sound using a cell phone as the car approaches and as the car passes him, right? Okay, so number 1, for this investigation, write down the following. A dependent variable. Obviously, the frequency observed must be the dependent variable, because that's what being measured as the car is changing its movement, right? So it moves from point A to point B towards him, and then from B to another point away from him. The learner records the frequency. And then 1.2, controlled variable. So you would notice that in most instances when you're doing Doppler effect, your value of V stays the same for your different questions, right? So it's safe here as well for us to say the speed of sound in air. So the speed of sound in air is going to be our controlled variable, because it's the one that we are ensuring that it stays the same, right? Okay, now a suitable investigative question for this experiment. Remember, when you're conducting an experiment, you have your variables, and your investigative question must ask mainly about the relationship between the independent and the dependent, right? So our investigative question can ask, what is the relationship? What is the relationship between the observed frequency, which is the frequency that we observe? What is the relationship between the observed frequency relative to the speed of the car, vehicle, or race car? So we are asking ourselves, how do these two relate? How does this one affect that one, right? So yeah, that is your suitable, or that is a suitable investigative question for this experiment. Okay, so the next question says, when playing back the sound recorded on the cell phone in the presence of an oscilloscope, a difference in frequency of 67,15 hertz was registered. So the difference in the frequency was this much. So this means that the frequency calculated after subtract the frequency calculated when the car was approaching him, the difference was given as that, right? Okay. Use the information above to calculate the speed of the race car. Take the speed of sound as that. Now, let's have a look at this. So this is to say the final frequency subtract the initial frequency. This must give us negative that, right? Okay, when I substitute, I'm going to say V divided by V plus Vs multiplied by Fs minus V divided by V minus Vs multiplied by Fs. This must give me negative 67,50. This is going to give us the frequency when the sound source was moving away. This is the frequency when the sound source was moving towards, right? Let's substitute this. So this is 340 divided by 340 plus Vs multiplied that by 200, which is given here, minus 340 divided by 340 minus Vs multiplied by 200, and then this is going to be negative 67,50, right? Okay, so we are going to work that out, and the velocity of the source is going to be, so that's, this can be taken out as a common factor, and then I'll say 200 divided by 1, then times that one, and that one transpose that one, and our answer is going to be 57,02 meters per second. So that's how we are getting our answer for the second question. I'm just going to quickly explain what just happened. It says, when playing back the sound recorded on the cell phone in the presence of an oscilloscope, they recorded a difference of 67,50, meaning that the final frequency subtract the initial frequency had a difference of what? Had a difference of this much. This is why I set up this equation to say the final frequency, which is the frequency when the sound source was moving away, subtract the frequency when the sound source was moving towards, must be equal to negative 67,50. Okay. Next question, still from the same paper, of course. The spectrum of light from most stars contains lines corresponding to helium gas. Diagram A shows the helium spectrum as observed in the lab. Diagram B shows the helium spectrum of light from a distant star. Now, when you compare the two, when you look at diagram B with reference to diagram A, you can clearly see that diagram B is shifted towards longer wavelengths, right? And when wavelengths are longer, we know that the distant star is now moving away. So the question is saying, is the distant star moving away from or towards the Earth? So the distant star is moving away from the Earth, right? Now, why are we saying it's moving away? It is shifted towards longer wavelengths. And we know that when the wavelength is long, it means that the frequencies are what? The frequencies are lower. So longer wavelengths and lower frequencies, what does that imply? If the wavelengths are longer, then it means the waves are stretched out, and therefore the star is moving away. So it's going to be, you'll get a mark for saying away and then the other 2 marks is for providing an explanation. The next question I want us to look at is from the Northwest September of 2022 question paper, and we are looking at question 6. It says, scientists studying the social interaction of dolphins in captivity connected an underwater sound recorder to an oscilloscope and immersed it in the dolphin tank at an aquarium. They recorded the sound waves emitted by the dolphins as they approached the microphone. The waves they recorded on the oscilloscope are represented below. Now we can see the waves here. We can clearly see here, that's the period for one complete wave, 2, 3, 4. So it means all in all, there's 4 full waves, right? Okay, without wasting any time, let's get into the questions. State the Doppler effect in words. Like I said, this you can easily pick up from your examination guidelines of 2021 and collect your 2 marks. Next. So there's your Doppler effect. You don't have any challenges here, I hope. Let's move on to the next question. The next question says, the average frequency of the social vocalizations of these dolphins is 38 kilohertz. Okay. So 38 kilohertz. So 38 kilohertz is obviously 38,000 hertz, right? Because you know that when it comes to a kilo, you multiply by 1,000 or you multiply by 10 to the power of 3. The question says, show by calculation that the frequency recorded is 2 kilohertz higher than the actual frequency. So this is the actual frequency, but we are told that the frequency recorded is 2 kilohertz higher. Okay. So if the frequency is 2 kilohertz higher, it means whatever calculation we perform, the expectation is that we either get 40 kilohertz or we get 40,000 hertz. Now let's take a close look at our graph. We are saying that to move from here to there is one complete wave, right? And this part over here is half of this. So half of 5 is going to be 2,5 times 10 to the power negative 5, right? So I can use this point to calculate my frequency. I can say the frequency is going to be 1 over period, which is 1 over 2,5 times 10 to the power negative 5. Let's plug that into the calculator and hope for the best. This is indeed 40,000 hertz, which is 40 kilohertz, and 40 kilohertz minus 2 kilohertz gives us what? 38. So that's fine. Alternatively, you can count and say 1, 2, 3, 4. And instead of using this, you can easily say 4 over 1 times 10 to the power of negative 4, because this is the amount of waves you have. 1, 2, 3, 4. If you want to use this point, you'd count the number of waves you had is 1, 2. So for this one, it would be 2 over 5 times 10 to the power negative 5. They all give you the same answer. Okay, so question 3, we are asked to explain why the recorded frequency is higher than the actual frequency. You'll remember here that the information said the dolphins are approaching the microphone, right? Now, when the dolphins approach the microphone, the waveforms are more compressed. So we are going to say waveforms are more compressed. And what does this imply? When waveforms are more compressed, it simply means that there are now more waves per second. There are now more waves per second. And if there are more waves per second, then there's going to be a higher frequency. So yeah, because we were told that the dolphins are approaching the microphone. So if I had to express it as a diagram, this would be what's happening. So this part over here, because the dolphins are approaching the microphone. Okay. So next question says, calculate the speed at which the dolphins are approaching the recorder. The speed of sound in water is 1,500 meters per second. So we have the frequency, which is 40,000. We also have the frequency of the source, which is 38,000, right? So now we need to work out the speed of the dolphins. So FL is going to be V plus minus VL over V plus minus VS multiplied by FS. What is our FL? This is 40,000 equals 1,500 divided by 1,500 minus VS multiplied by 38,000. So this is going to say 38,000 times that divided by that minus that. And the speed at which the dolphins are moving is 75 meters per second. Now, this is how you're obviously going to get marked. It's 1 mark for the formula standard, and then 1, 2, 3, 4, 5. And then that will be it. Next question. Astronomers have used Doppler effect to conclude that galaxies are moving away from the Earth. Write down a reason to support their conclusion. Now, this is obviously redshift, blue shift. Redshift explains that the universe is expanding, right? So the reason why astronomers are concluding that galaxies are moving away from the Earth is that when light is observed from a distant star, right, it shows longer wavelengths. And when the wavelengths are long, we know that the frequency is shorter or the frequency is low, right? So the frequency is low frequency. And what does that imply? This implies that it is shifted towards what? It is shifted towards the red end of the spectrum. So this is shifted towards the red end of the spectrum. That's what it means. So yeah, so when you're observing light from a distant star, you would observe that it has longer wavelengths. If the wavelengths are longer, it means the frequencies are low. And when that happens, it means the light is shifted towards the red end of the spectrum. And therefore, that explains that the galaxies are indeed moving away from the Earth. And that is 2 marks, of course. Okay, so let's quickly speak about what we touched on. So we did calculations. You saw what happens when a sound source moves towards. You saw what happens when a sound source moves away. And we also looked at how to work out simultaneous equations when you are given these scenarios happening at the same time. You also learned, or you saw how to calculate frequency when given a graph. Very important knowledge there. And then we also looked at the applications of Doppler effect to say in medicine it's used for this, in law enforcement it's used for this, and in astronomy as well. So yeah, I hope as far as Doppler effect is concerned, you are now better prepared to tackle your exams. So in the next lesson, we are going to be covering chemical equilibrium, which is paper 2. We are going to be covering chemical equilibrium, which is paper 2. Chemical equilibrium, we are going to look at calculations. So calculations will include KC calculations, of course. We are going to look at factors that affect equilibrium. So these are factors that affect equilibrium. And I hope you obviously know that these factors are your temperature, concentration, and pressure. And pressure is subjected to gases only. And then we'll also look at factors that affect KC. Factors that affect KC, and this is obviously temperature only. It's very important. And then we'll also interpret graphs to see what happens when certain changes are effected, what happens to the equilibrium position in terms of graphs when certain changes are effected on the graphs, of course. Thank you for watching this lesson. See you next time. Goodbye.